Happy day and welcome everyone. So today we're talking about Coulomb's law and a little bit of an introduction to photoelectron spectroscopy or photoemission spectroscopy. So let me just start off by who this guy Coulomb was. So he was a French physicist. He lived actually in the 1700s-ish, and what he was studying was, and what he's most recognized for, is he was studying the electrostatic attractions and the interactions between things that were electrically charged. And he came up with some incredible things that we not only used in chemistry, but we also use heavily in physics. And so I just want to take you through some of the basic stuff of how his law applies here. And we're not necessarily going to be using his equation to do calculations in this course. Instead, what we're going to be doing is using it more conceptually to try to get an idea of how it is that atomic particles are interacting with each other. Now, let me start off by saying, when is this useful? So there are two major times where we use his equation, but it shows up over and over and over again in the College Board framework. And so it's really important that we do understand Coulomb's law. It's also very useful in a lot of different FRQs and a lot of different essays. So let's get right to it. So in the original form, it is this F equals K Q1 Q2 over R squared, where F is simply the force that an object exerts on something else. And Newton's third law simply states the force exerted by one particle on another is equal in both directions. K is simply a constant, and that's equal to this 9 times 10 to the 9th newtons times meter squared per coulomb squared. Again, that's the notation that they use on the AP, is this negative. Each Q is simply the electric charge, okay? So this is really important. When you look at Q1 and Q2, it's simply representing charges. Usually what happens when we're talking about an atom, though, is we're Q1 and Q2, you'll have two different compounds that you're looking at, and so usually you're comparing those two compounds. So Q1, it might be something like KCl, where you would say that the charge on the K on the potassium ion is a +1 and the Cl is a -1, versus something like, I don't know, maybe barium sulfide, where we have barium as a +2, but sulfide is a -2. And so that's what we're going to be talking about when we're looking at charges, and we're going to typically be comparing two compounds when it comes to chemistry. R is simply going to be the radius or the distance that's between the two objects. For chemistry, we use a modified version of Coulomb's law, so this is what I was explaining to you, derived through basic physics and calculus. We also only need to understand how the equation works conceptually. You will not need to solve for E mathematically, just as I had said before. So what is this E for? Well, typically what this E is for, it's actually for two things. In this unit that we're going to be using this, we're going to be using E as our ionization energy, but the other thing that it can be used for is called the lattice energy. So we will be using it for both in this year, and we'll come back to Coulomb's law later on as well. Okay, so E, we said, is called the lattice energy between the two objects, and R is simply just going to be what we would say is the square of the distance between the two. And now again, we're talking about the nuclei of the atoms. The equation suggests that two ions of the same charge will move as far away from each other as physically possible. Why? Because we know that, yes, opposites attract, but like charges should be repelling each other. So we're going to try to be as far apart from each other as possible. Should be as far apart as possible to achieve the smallest amount of energy, as nature tends to follow the path of least resistance. However, it says at extremely short separations, two ions will start to repel each other due to the strong positive charges of their nuclei. So don't forget that in the center, there's a nucleus, and that nucleus is charged positive, and so that's going to have a huge factor when it comes to Coulomb's law here. The most important application of Coulomb's law is the energy between an atom with a positive charge and an atom with a negative charge. A negative energy means that the particles are actually attracting each other. A positive energy indicates that the particles are actually repelling each other. As the atoms get closer, the energy between the atoms grows greater as the force attracting the particles to each other also increases. Let's take a look at this, okay? So what they're calling this y-axis is they're calling it the potential energy, and they're using kilojoules per mole. Now we have our baseline here, And so this baseline is kind of our separation between positive and negative. So we can see here that positive is indicating a repulsion and negative is indicating an attraction, okay? So what happens is when you have your atoms, and by the way, what our x-axis is referencing is our internuclear distance. Internuclear. What that means is inter simply means between, and nuclear means the nucleus. So it's a distance between the nuclei, okay? So you have two atoms, and then you have the distance between the two nuclei. So what this basically is showing us is we've got our two hydrogen, this is just hydrogen gas, and so diatomic, and this here is where they are basically as close as they possibly can be to each other. So this is where they're super close to each other. And now we know that it's experiencing a repulsion, okay, because those nuclei are so close that they're going to start repelling each other. Now, let's go to the far end. Let's go to the opposite end here. This is really where they're as far apart from each other where they're really not attracted to each other anymore. So this is kind of trying to show us that if we kept separating them, then there really isn't an attraction. And so there's a really nice simulation that you're going to be doing that should be helpful with this as well. Now, what is this part called? This down here is really called our sweet spot. This is the perfect distance between the nuclei, okay? And so we really look at this value, and this value right here is super important. That is our bond enthalpy or our bond energy. That's the amount of energy that it would take in order to separate those two atoms, those two nuclei from each other, okay? Or those two atoms from each other. All right, so now it says the depth at the lowest energy in the potential energy curve above represents what we are looking at, represents the bond strength. And the distance at the lowest energy is called the bond length. So that is what it is giving us, is called the bond length. Using Coulomb's law and the bond length, one can predict the strength of an ionic bond. Based on Coulomb's law, we note that ionic compounds formed by ions with larger charges, well, if they have higher charges, then that should be a stronger bond. So that should create a stronger bond. So it's almost like having two rubber bands versus one, or three rubber bands versus one surrounding two things. So the higher your charge, the greater your charge difference, then the stronger that is. Well, what happens when you have more rubber bands? Well, those should actually have stronger bonds with shorter distances. So shorter distances also should form stronger bonds. Okay, so what is it that we can take away from this equation? So we know that force must be directly related to the magnitude of both charges. So we're going to say it's directly related. The other thing is that the force is blank to the square of the distances. Well, what did we say? How is force related to the distance between the charges? Well, if we look at our equation, it's E is equal to K, Q1, Q2 over R squared, which again, we usually use a D, or we can use an R. And so then we say that they're related how? Well, as one goes up, the other one must be going down. So then we say that they are inversely related to each other. If the two charges have the same sign, positive or negative, then the force is repulsive. If they have different signs, then the force we say should be attractive. And if it is attractive, then we would say that our energy, our sign of our energy should be negative. Okay? Why does Coulomb's law even matter? So in an atom, you have the nucleus, and it says it's held together by what we call it is, this is one of those things that is kind of like the way that gravity is. It's not really something that we can explain, but what they call it is they call it the strong force. Okay, good, really good to know this. It's called the strong force. We don't totally understand it because we know that the nucleus, everything inside of the nucleus is either positive or not charged. And so what really holds that nucleus together? We can't say it's the electrostatic attraction because that would be opposite charges like the positive nucleus with the negative electrons. But what's holding the nucleus together is called the strong force. And a lot of times they just call it the nuclear force. And the electrons are moving around it. What keeps these electrons from leaving the atom? Well, that's the electrostatic attraction. They're attracted to the protons in the nucleus as Coulomb's law predicts. The major application of Coulomb's law in AP Chem is calculating ionization energy. So just like I had said, when we look at that equation, E equals K Q1 Q2 over R, that E is also for ionization energy. What is the ionization energy? It's simply the energy that is required to remove an electron, to pull an electron off. So ionization energy is the energy that is required. And so what I want to make sure that we know here is that what is the sign of ionization energy? Ionization energy is always going to be positive, okay? And typically it's going to be a big positive number. And the reason why is because no matter what, whether an atom will become more stable or not, an electron belongs to a particular nucleus and to a particular atom. So to remove an electron away from that positive charge, it's always going to fight you, okay? And so that is always going to be positive, meaning that it requires energy, or energy needs to be absorbed in order for that to happen. Why is ionization energy related to Coulomb's law? So the protons in the nucleus attract the electron, so taking away an electron is going to require some energy to overcome that attraction. Naturally, all other things being equal, we'd expect a higher ionization energy to correspond with a nucleus that must be stronger or larger. So, and we usually say stronger because the nucleus, as far as the size is concerned, they're always like pretty close in size, but the more positives you have, the more protons you have, the stronger your nucleus is going to be. Since that larger nucleus would have more protons and thus more positive charge. So exactly just what we said, more protons, more positive charge gives us a stronger nucleus. In fact, that's one effect that we see. We'll look at a diagram in a moment. However, we'll also see an effect mediated by the R term, distance. Now, what I need to tell you is that you always need to make sure that you look at your charges first. The charges are definitely going to take precedence when it comes to Coulomb's law. So what you do is you look at Q1 and Q2 when you're comparing two compounds, for example. If Q1 and Q2 are the same, then you need to look at your distance between them. In other words, then you would look at the size of the atoms, okay? Otherwise, don't even look at the size. The charge is going to take precedence in this situation. You see, because of quantum mechanics, electrons move around the nucleus in those discrete shells with a certain amount of probability. So we know that it's all based on a certain amount of probability. You've almost certainly encountered them already, so we know this: 1s2, 2s2, 2p6, 3s2, for example. For nitrogen, we'll have 2 electrons in the first shell. So we can see here, we've got our 2 electrons. And again, even though this looks like Bohr's model of the atom, we're just talking about the shells right now anyway, so outside of the nucleus. And then in the second energy level, well, the rest of them, we've got another 2s, but then we have 3 in the p. And so we have a total of 5 electrons in the second shell. And because the distance is greater to the electrons in the outer shells, Coulomb's law indicates that the ionization energy is going to be lower. So in other words, the closer the electrons are to the nucleus, the stronger the effect of this nucleus will be. And so these electrons here have a stronger pull because of this positive charge. And we've got our 7 protons that are in the nucleus. Those 2 in the inner sphere shape, those are going to be drawn closer. And then that second energy level, even though we have a 2s and a 2p, they typically say that those are a similar distance from each other. So because the distance is greater, the electrons in the outer shells, Coulomb's law dictates that the ionization energy will be lower. It's important to note, however, that 2s and 2p may appear to be in the same shell. The 2p is slightly further out, so their ionization energies will be slightly lower. Okay, so we do fill the S before we fill the P, and same thing when the electrons come off, the P actually will come off before the S. Okay, let's look at a simplified ionization energy chart for nitrogen. The most common way to look at ionization energies is through what is called photoemission spectroscopy, or PES. Essentially, they fire photons of a certain energy at an element, and they see how many electrons end up coming off. So this is known as the photoelectric effect, and this Einstein actually got a Nobel Prize for this. We also now use this effect to create streams of electrons or current from photons. In other words, this is really even how solar panels work. Okay, so the important idea underlying photoemissions, or PES, photoelectron spectroscopy, is if an atom is struck by a photon with at least the same amount of energy as the ionization energy, then that electron is going to pop off and we would say that that atom is now ionized, okay? Because ionized simply means that you formed an ion, a particle with a charge. But this is also important. If the photon doesn't have enough energy, the atom will not be ionized. So even if it's struck by a whole bunch of low energy photons, it does not matter. You need that ionization energy, that minimum amount. Once you do that, then you can ionize the atom, okay? What does this mean for PES? So essentially, we can pin down what ionization energies are for that atom, because below that energy, nothing happens. And then above that energy, those electrons can be knocked off. Okay, does it make sense? So we're talking a little bit about Coulomb's law. So like charges repel, opposites attract. The force is proportional and then to the magnitude of the charges, but inversely proportional to the square of the distance between them. Again, our equation is simply E equals K, that constant, Q1, Q2 over D or over R squared. Again, in chemistry, we kind of use a variation of that. Ionization energy, an application of Coulomb's law, position of the peaks in the PES graph. Horizontally, we're going to look at one of these graphs, which shell the electrons are in, the size of the peaks. These denote how many electrons are in that shell, so we're going to take a look at that in just a second. And then again, PES. Photons of a certain wavelength are fired into atoms of an element, and they either knock off the electrons or don't. It depends on whether they have met that minimum energy requirement. Okay, what does it look like? All right. This is an example of a photoelectron spectrum for nitrogen. So we know that nitrogen is 1s2, 2s2, 2p3, okay? And so we know that it has 7 protons, and so if it's a neutral atom, then it should have 7 electrons, okay? And we're not worried about it being diatomic right now. So we want to make sure that we know how to read these. And so we're going to take a look here. Actually, let's just go right through the list. So how do we read it? So the first thing that you always want to do is you want to make sure that you check the x-axis. Here's why. They can flip it on you, okay? I know it doesn't seem right, but they can. If you take a look at this, the way that this is set up right now is this is 100 and this is 0.1, which means I'm actually decreasing as I'm going across. This is showing a decrease in energy. Is it common? Well, really, they can do whatever they want to, okay? Why does this make sense? Well, because the reason why this makes sense is they're actually starting at the nucleus and they're looking at the electrons closest to the nucleus and how much energy would be required to remove those electrons, and then they moved out. That's not normal though, okay? So what normally happens is you pull off the outer electrons first, and then you start moving in towards closer and closer towards the nucleus, okay? And don't forget, this is really important too. The more electrons you pull off, the atom actually gets smaller and smaller. And simply by pulling one electron off, you can even decrease the atom size by half. Okay, by half. Okay, so check the x-axis. Again, we said it can be increasing or decreasing. All right, and sometimes the diagrams, they can have them stacked just because it's too hard to go across a page, so they kind of truncate them and stack them. Okay, now the highest binding energy. The highest binding energy, when you find the biggest number on your x-axis, what is that representing? That's actually representing the electrons that are the closest to the nucleus, okay? So keep that in mind. All right, let's take a look at the y-axis. What does it read? Well, it reads relative number of electrons, okay? Relative number of electrons. It says, observe the peaks. So starting at the highest binding energy, start your electron configuration. And that's going to be the easiest way to figure out what your ticks actually mean too. So it says 1s2, 2s2, 2p6, 3s2, and so on. Note 1, sometimes there's a squiggly line. And there may be a big energy gap, and so that's why they'll have a squiggly line. The other thing, again, I had said is sometimes they're staggered, and so you can sometimes we'll stack the graphs, okay? So number 4 says, ensure the peak heights match the relative number of electrons. So let's take a look at this, and I'm going to try to just explain it based on the graph here. Okay, so I know that where my highest number is, which is right here, should be closest to the nucleus. So that means that this should represent 1s2, okay? So if that's the case, that means that this represents 1 electron and this must represent 2 electrons, okay? So you want to label that. They won't have that labeled. Usually they won't have that labeled. So you want to go in and label that yourself, okay? So then that means that this must also be 2 electrons. Well, then what does this represent? Well, if that's 1s2, then this must be 2s2, okay? Well, then what is this? Well, after I go 1, 2, then this must be 3. So this must be my 2p3. And so what you can do is, if you didn't know this was nitrogen, which usually that would kind of be the game that they would play with you, is they would say, what atom is being represented here based on the PES, based on the photoelectron spectroscopy graph, okay? All right, so number 4 just says ensure the peak heights match the number of electrons. And so this just kind of explains a little bit of what I did and about the peaks. So you can just kind of take a look and read through that. And there's another Bozeman video that kind of goes along with this too. All right, so let's answer some questions here. Now, I want you to think about this a little bit. So if you want to pause and try this out yourself, the answers are on the bottom of the page as well. First question says, based on Coulomb's law, which of the following cations is most likely to have the strongest interaction with an adjacent water molecule in an aqueous solution? Now, it doesn't matter that it's water. What you're looking for is you're looking for something with the highest charge, okay? Because the highest charge should have the strongest interaction. So then what I'm going to do is, I guess I'm going to get rid of sodium, okay? But that's not really helping me here. So now the next thing that I want to do is I want to take a look at the location on the periodic table. Now this is going in order, so it's going from beryllium to magnesium to calcium to strontium, and these are all right down the alkaline earth metals. And so based on this, based on my equation, E equals K Q1 Q2 over R squared, well, what I want is, if I want the one with the strongest, I want my E to be the highest, then that means that I actually want the smallest distance. I want the lowest distance. I want my charge to be the highest, okay, but I want my radius or my distance to be the smallest. So if I'm going down the periodic table and strontium's at the bottom, we know that as you go down the periodic table, these atoms get bigger and bigger, okay? So that means that beryllium, A, must be the best choice here. Okay. According to Coulomb's law, the energy between an ion pair is inversely proportional to which of the following parameters? Again, we already know this. It must be the distance of separation. The distance is inversely related. Question 3. Which of the following is true about ionic compounds according to Coulomb's law? Okay, so it says ionic compounds formed by ions with smaller charges form stronger bonds. That's not true. We actually want bigger charges. Ionic compounds with longer bond lengths have stronger bonds. Well, if there's a longer bond length, that actually means that it's weaker. So the longer it is, the weaker it is. So again, think about the rubber bands, like I was saying about the rubber bands. So no, I don't want it longer. Ionic compounds formed by ions with larger charges and longer bond lengths lead to stronger bonds. Oh, we were almost there. We want larger charges, but we want shorter bond lengths. And so this one says ionic compounds formed with ions with larger charges. Yes, that's the one we want. Okay. Which has a higher first ionization energy, lithium or sodium, and explain using Coulomb's law. Okay, so the first thing you always want to do is you want to start by saying E equals K Q1 Q2 over R, so that you're sure that whoever the reader is knows that you know what Coulomb's law is. Okay. Now, lithium or sodium are both alkali metals. So since they're both alkali metals, they both have the same charge. So if I'm talking about ionization energy, they're both going to form ions with the same charge. Okay. So it would be like Li plus or Na plus. So instead what I need to do, and both of these are actually neutral anyway, so they're not even charged. So I shouldn't even be looking at that. The only thing I can really look at right now is my distance between them. So again, since I know that my distance is inversely related, if I want the higher first ionization energy, I actually want the one that has the smaller radius. And again, as we go down the periodic table, it goes hydrogen, lithium, sodium. So then I know that lithium, since lithium is smaller in radius, then it must have the higher first ionization energy, because according to Coulomb's law, that must have a stronger attraction. The nuclei have a stronger attraction. So the ionization energy, which is the energy required to remove an electron, must be greater. So the energy to remove an electron must be greater. Okay, and there are so many ways that you can basically phrase this, okay? All right, and this last question here, and this is from the AP framework. So this is showing the relative number of electrons. We can see here that, again, it's decreasing, going across my x-axis. This is actually getting lower and lower, which means this 700 would be representing electrons closer to the nucleus, okay? And so again, I see the same thing here, 700 to 300. This peak is further to the left, okay? And so they're giving me nitrogen and oxygen. So, by the way, I also wanted to make sure that we kind of just make note of where they are on the periodic table so we can see that it goes nitrogen and then oxygen is a little bit to the right there. Okay, remember what this is meaning here, what this means to me is this means that this must require more energy to remove. It requires more energy to remove this electron from oxygen than it does from nitrogen. Okay, let's just take a look at the answers here and see what makes sense. So let's just jump right into it. First thing says nitrogen atoms have a half-filled p subshell. Okay, here's the thing. Half-filled means it's a little bit more stable. And so that kind of doesn't make sense because that would mean that nitrogens should actually be higher than oxygens, but it's not. Oxygens is higher. There are more electron-electron repulsions in oxygen. Well, the more repulsions you get, the further out they are. And if they're further out, then those should be easier to remove. So, not sure about that. Electrons in the p subshell of oxygen provide more shielding than electrons in the p shell. Well, shielding is the distance from the nucleus, and so really they should be the same distance from the nucleus because they're both in that 2p, so that doesn't work either. And the last one says nitrogen atoms have a smaller nuclear charge than oxygen atoms. Oh, wait, what? Yes, so they have a smaller nuclear charge. In other words, nitrogen has 7 protons, whereas we know that oxygen has 8 protons. And so since it has a smaller nuclear charge, the oxygen atoms are going to be pulling in a little bit, tiny bit closer. Okay, and so hopefully that was helpful for you. That is Coulomb's law and PES. And by the way, just to kind of give you an idea, this explains a little bit of like how to do the calculations if you were interested. But again, we're not using the equation. Happy day, everyone.